Hi there, my name is Aaron Lanterman. In my last video, I started exploring a new language for music called Sound as Pure Form, abbreviated SAPF. I didn't really get that far in that video, I just installed it and tried out a few of the examples. But this video turned out to be rather popular. There's a distinct knee in the curve here around 2 days in, which I think is the result of this video being posted to Hacker News. So I would like to thank user Mindcrime for that. So let's start looking at the language. SAPF is a stack-based language. So instead of saying 3 plus 5, you would say 3, 5 plus, and that will give you 8. Let's break that down a little bit more. We can push 3 onto the stack, push 5 onto the stack, and then when I use the plus operation, it pops the top 2 entries on the stack, adds them, and pushes the result onto the stack. If I want to take what's on top of the stack here and duplicate it, I can use the AA operator. Let me put something else onto the stack. How about 10? If I want to swap the 2 elements on the top of the stack, I can use the BA operator. And there's a lot of operators like that. Clear clears the stack. Now, I can also use a back quote on the plus, and instead of applying it directly, it pushes that function onto the stack. I can then use the exclamation mark operation to apply the function on the top of the stack. So that gives me 8. And I could write it like this. I could then say that we can assign variables, and the notation here takes a while to get used to. So I'll write 5 equals A. Now you're used to seeing the variable on the left. Here it's on the right. If I ask what's A, it will push that onto the stack. So I can keep pushing A onto the stack here. Now in a program like MATLAB, I'm used to just looking at a variable by typing it. Here I have to remember it's adding it to the stack, so I wind up using the clear operation a lot. Now let's break this down a little bit more. I could push 5 onto the stack, and I see that this equals A operation, what it does is it takes the top value in the stack, pops it off, and then assigns it to A. Now, I cannot do this. I can't put equal on a separate line. It gets upset. So this is a special form. That's just assigning 5 to A again. So I can say 3A plus, and that will give me 8. I have lists in the language, and these are fairly flexible. So I could have the number 3, I could have the string dude, and I could even have a function, maybe the sine function, and it's now pushed that onto the stack, that particular list. Notice 8 was already on the stack. I also have a special kind of list called signals. Now, if I try to do the same thing with this pound sign notation in front, I guess you call it the hashtag nowadays, it won't work quite the way I expected because signals can only have floating point values. So I can do 3, 2.9, minus 0.7, something like that. Okay, let me clear the stack. One thing I'll mention is that if you don't put a space, it will compute the fraction for you. So I can do something like that. Now, if I try to do that without the space, this is now going to be a division operation on the 3 and the 1, and this is going to be a division operation on 2 and 9. Now, here's something fun. We have infinite lists. If I type nat, that will give me the natural numbers, all the numbers starting at 0. If I want to get the ordinal numbers, which are the numbers starting at 1, I could take that list, notice it's already pushed onto the stack, and I could add 1 to it. Now I also have the ordinal numbers built in with the ord command, so that will push that onto the stack. And if I want, I could add these two things together. Of course, these infinite lists aren't really taking up infinite memory. These are what are called lazy lists, or sometimes they're called streams. Basically, there's a mechanism to create the next element you need that you can then execute as needed. So this language is called Sound as Pure Form. Let's generate some sound. Let's take a look at the saw command. So I'm going to use the back quote on saw and say help. So we'll see that saw is a function that takes a frequency and a phase, and it's going to produce a stream for a band-limited sawtooth wave. Now, let's break this down. When I type that back quote saw, it pushed the function onto the stack, and executing help gives me the help. If I try to do it without the back quote, it's going to try to run saw first as a function, so that doesn't work. That's why I need this back quote. Okay, let's make a 220 hertz wave with 0 phase. So what this will do is it will push 220 and 0 onto the stack. The saw operation will pop this off and push onto the stack the signal for a sawtooth wave. I have the hashtag in front here that tells me it's a signal. Now, we can run the play command to pop that off the stack, play it, and then I'm going to use the stop command to stop it. That was a little loud. So this time, let me put the play on the line here. And what we'll do is we'll multiply it by 0.25 so it won't be so loud. Let's try to turn that down even more. So sapf code can be difficult to parse if you don't know what the arguments of the functions are. We can make this a little clearer by using some parentheses like this, but they aren't necessary. The README file doesn't really talk about the parentheses. I think it does enforce precedence. I think what's happening is it will run this on a clean stack, include the result here, then run this on a clean stack, include the result here. Notice if I did something like this, that still works by the stack mechanics, although it definitely doesn't help with the readability and understanding what's going on. Let me try doing something like this. I think this will crash out because it's going to try to run this star operation here for multiplication on a stack that only has 0.1 on it. So I think this is going to complain at me. Yeah, it complains at me. Hi, so Camtasia crashed on me, and then when I tried reopening my file, it hung. So I shut everything down, rebooted the computer, and then fortunately, the project did open. So let's keep going. Let's see. So we had something like 220, saw. Let's do 0.5 times and play. Okay. Now here's something cool that you can do. Instead of just putting the 220 hertz here, let me put 110 and 220 in a list. This will do a multi-channel expansion. And to really see what's going on here, let me do this. So we'll see that we have a list, and the list contains two signals. So one will be a sawtooth that's 110 hertz, the other 220 hertz. And now if I play that, that comes out as stereo. Pretty cool. Let's try that again, but this time let's make these pretty close in frequency. Actually, let's do that and put play on the same line. Now, what if you want a sine wave? Well, Sin is just the regular old-fashioned sine function. If you want to generate a sine wave easily, then you can use the sinosc command. So let's do 220 sinosc. Let's play that. And if we ask for the help for sinosc, we see like the saw, you give it a frequency and a phase. Let's see if we can do frequency modulation. Now, DX7 style frequency modulation is actually phase modulation. So let's put another sine oscillator in the phase spot. Let's see what that sounds like. Okay, let's decrease the index of modulation by multiplying it by 0.5. And to try to make it clear what's going on, I'll use parentheses here, but I don't need them. Okay, now let's turn the index of modulation up. Okay, that was exciting. Let me get that 0.707 off the stack. Okay, let's see if we could sweep the index of modulation. Let's look at the help for LFO. Frequency, phase, low, high. Okay, so let's try an LFO with the frequency of 0.1 hertz. We'll have a slow sweep. Let's try 0 phase for now. And let's say 0 to 10. And this is an LFO. And let me make sure I have things matching up. All right. Okay, so that started full blast. I want it to ramp up. Let's see. So if this LFO is a sine wave, then the LFO will already be starting halfway up. I want it to start at the bottom of its range. So let me try something like minus 0.5. And I think I can multiply by pi by just putting pi here without a space. Okay, that did not start at the bottom of the range. Oh, you know what? I wonder if instead of a 0 to 2 pi convention here, maybe it's using like a 0 to 1 convention. So maybe let me try minus 0.25. Okay, that sounds more along the lines of what we're looking for. Let's try 55 here. Now, if I want a smaller segment, what you can do is you can give it whatever you're playing, and then you can give it 10t. What this will do is it will play a 10-second segment. All right, let's see if we ask for help on the T command. We see it takes a signal and then a time, and it returns the first T seconds. All right, let's see if we can plot a spectrogram. Not sure what dB floor is. Okay, I just looked through the examples, and they use a structure where they have 100 for the dB floor, and then the file name is 0 sgram. Oh, whoops, I lost the T. So I was trying to take the spectrogram of the number 10. All right, let me put the T back in. Oh, it appeared on my other screen. Let me drag that over. There's a spectrogram. Now, did that create a file? Probably not. This 0 probably means don't output a file. Let me go look. Nope, I don't see a file. Let's try that again, and I'll put my spec here. Huh. Maybe it wants me to manually create a spectrograms folder. One moment. Okay, I now have a spectrograms folder. So let's try that again. Aha! So it opened it up, and it looks like it's called myspec100. All right. And let me see if I can actually find that folder. Ah, and here's that file. All right, so it looks like if you put 0 there, it just creates a temp file somewhere. Let's play with that channel expansion. Let's put 220 hertz for our carrier in one channel and 110 hertz in the other channel. All right, now let's try doing that sort of expansion with the modulator. So here it is with 220 hertz, and we'll put a modulation of 55 hertz in one channel and 110 in the other. Okay, let's try both. So what we'll do is let's have 220 in the first and maybe 110 in the second for the carrier, and then we'll have 55 and 110 for our modulators. How about let's take the second modulator and put it down at 25. I could do this all day. So in the next video, assuming I keep going with this series, we'll look at functions and forms in sapf. But before I close out this video, there's something I wanted to mention about assignment. We could assign 1 to A, 2 to B, and 3 to C. But if you remember the semantics, this assignment operation just grabs the thing on the top of the stack. So I could push 1, 2, 3 on the stack. This will pop the 3 off and assign it to C. And then I'll just have 1, 2. And then I could assign B. And then I could assign A. Now, if I were to say A, B, C, that would push A on the stack, then B on the stack, and then C on the stack. So I could do something like 1, 2, 3 is equal to C is equal to B is equal to A. But that would be a little difficult to read. There is a special semantics associated with parentheses on the right-hand side of an equal sign. So I could do this. So I can write A, B, C like that, and then it will assign 1 to A, 2 to B, and 3 to C without having to read this kind of reverse notation. So the parentheses here are operating differently after the equal sign than the parentheses that I was showing before that were indicating some kind of precedence. Okay, I said that business with the multiple assignment was the last thing I was going to talk about here, but there's something I want to try. What if we didn't have this sinosc command? What if we had to construct that from scratch? Well, I have the ordinal numbers. No, I don't want that. The natural numbers. There we go. Let's start with 0. Now, we can't play lists. We have to play signals. But there's a version of all of these things where you put a Z on the end. That will give you a signal. So let's take the natural numbers and let's multiply by our frequency 220 hertz. And let's say I need to also multiply by 2 pi. And we need to divide by the sample rate, which is SR. And then I need to take the sine of that, and then we can play that. There we go. It worked. Oh, I just realized I forgot to turn recording system audio back on. Let's try that again. And I just learned that there's these other functions that will give you variations of the sample rate, including 2 pi divided by the sample rate. That's RPS. So I should be able to take nat-c, multiply it by our frequency, and then just multiply it by that RPS. Does this work? No, I need to take the sine first. There you go.